Thank you for coming to the lecture organized as part of the IMSC Open Day. So this is part of the Swachhata Pakhwara 2025. So this is a program which is taken up by the Department of Atomic Energy, which funds this institute as part of the Prime Minister's drive for a clean environment. So we'd like to acknowledge the generous funding given by the Department of Atomic Energy for organizing this. And you've already had some experience in doing pottery, which essentially is one of the earliest methods of having a sustainable material for building objects of daily use, and which also provides an extremely clean environment because they are all made of earth, and to earth they return. And we'd also like to point out that, and this is something that Evgenia, our ceramics artist who had given demos, had pointed out, that ceramics is one of those art forms which has a very strong component from science, physics in particular. And to shed more light about the physical aspects of ceramics, about how it beautifully demonstrates the interplay of forces, we have our own very postdoc, Dr. Soling Zimic, to give a talk on the physics of the pottery wheel. So just a few words to introduce Dr. Soling Zimic. So Soling did his PhD from the Department of Physics of the Indian Institute of Science, where he worked on the physical theories underlying heart arrhythmia. And he has also been involved in working on developmental pattern formations. Following a short stint in the US for his first postdoc, he joined the institute in 2021, is that right? And he has been working on, among other things, on biophysics and also on pattern formation. So without further ado, let me invite Dr. Soling Zimic to give his talk on the physics of pottery wheel.
So today I want to talk to you about the forces that are at play in the process of making pottery. So as I was preparing for this presentation, I was thinking about what could be the forces that are involved in the process and what could be their functions. After all, it's a mechanical process. You're molding a clay into a shape. So I thought understanding the forces behind it might be important in, sculpting the final beautiful structures. Then Evgenia was teaching us how to do pottery yesterday, and I heard her saying that doing pottery is all about the mind, nothing to do with the forces. So I don't know what use is my talk going to be in pottery making, but yeah. And also, one thing I have to say is that I've made the content very, very simple. So if any of you have any science background, it's going to be very trivial for you. So I apologize in advance. So let me begin by saying a few words about the geometrical symmetry that most of the ceramic objects seem to possess, and also the possible utility of this symmetry. So if you look at the objects here at the top panel figures, which are ceramic wares, some of them are used for decorative purposes, let us say, and some of them used in kitchen. So despite having distinct shapes and immaterial of whether they are used for decorative purposes or for storing food, most of them seem to have a common property, that is this axial symmetry. So what do I mean by that? If an object has an axial symmetry, as shown here, then there's an axis passing through the object, around which, if you rotate the object, you wouldn't be able to distinguish the initial configuration from the final configuration. So for example, here I have a clay cup. This has axial symmetry. So if I place it here, and then let us say I ask you to close your eyes, just saying you don't have to. And meanwhile, I rotate this cup, and then I ask you to open your eyes. You wouldn't be able to tell whether I've rotated the cup or not because of the symmetry. Or to put it another way, if you go around the axis of symmetry, the object looks the same. Right? So this is what I mean by axial symmetry. So I'm also going to call this as circular symmetry. So I'm going to use the word axial and circular interchangeably. Right. So, but it's not only the objects that are made of ceramics that have this symmetry. So if you look around the kitchen, the items that you own, most of them might have this axial symmetry. So for example, here, the objects made out of metal, and some of the collections from my kitchen here, some of the objects here are made out of plastic, glass, doesn't matter. So they all seem to have this axial symmetry. So then one asks the question, does this symmetry have any utility? Does this serve any purpose? One reason could be aesthetics. Probably symmetrical objects looks more beautiful than non-symmetrical ones. The other reason could be ease of making these objects. Maybe it's easier to make symmetrical objects than the ones that are not. But could there be another reason? And I claim that the answer is yes. It has to do with the maximum space offered by an object given an amount of material used in making that object. So let me elaborate that point by taking the geometry of a plate, the plate which we use to serve food. So if you look at the shape of the plate that you own in the kitchen, most of them are going to look circular. And the question is why? Right? So so if you're designing a plate, you would want to use the least amount of material to attain a certain amount of space, right? Or to put it another way, you would want to look for a shape that gives you maximum space for a given amount of material, right? So that's what you would look for if you are a manufacturer of plates. So it turns out that amongst the possible shapes that you can think of in 2 dimensions, let's say rectangle, a triangle, or any other polygon, circle provides the maximum space for a given amount of material used to make that object. Right? So this can be proved rigorously using mathematics, but today I'll just give you an idea as to why this is true. All right. So let's consider a circle and a rectangle, for example. A circle, you can find out the area. I hope this is not sophisticated math here. And then you can also find out the area of a rectangle. Now, let's assume that these two geometries, the circle and the rectangle, have the same area. That is to say that you use the same amount of material to make up these objects, right? After all, an area occupied by an object is the area occupied by the material making it up. So if you assume that, the claim is this, that despite having the same area, a circle will offer more space than the rectangular plate, which means you can place more food on a circular plate than the rectangular plate that has the same area. Right? So to understand that, let me make 2 statements, which are very obvious statements. So for example, statement 1, no space available at the boundary. I hope this is obvious, which means, when you take a plate and you try to place food, you can't place food at the boundary because there's no space available. The boundary is just a line, right? That's statement 1. Statement 2, longer boundary length implies you've used more material to make up the boundary. I hope that is also an obvious statement. So the consequence of these 2 statements is as follows. If I now take this rectangle and then stretch it, and I stretch it in such a way that I preserve the area of the rectangle, right? So as I'm stretching it, the length increases, but because the area has to be preserved, the width shrinks, right? So this rectangle, again, this can be proved mathematically, but I hope this visually it's convincing that this rectangle will have longer boundary length than this one, the upper one. Having a longer boundary length is bad because there's no space available at the boundary. You can't place food at the boundary, right? And also because it has a longer boundary length with the same area, you have used up more material in making up the boundary. So less material is available inside, which you could have used for placing food. So despite having the same area, the upper rectangle and the lower rectangle here, the lower one gives you less amount of space. This point becomes more clear if you do this thought experiment of stretching this rectangle on and on and on, so much so that it eventually becomes like a needle, right? So almost all the space has been used up in making up the boundary. So in that case, I mean, no matter what the area is, you wouldn't be able to place any food on that plate, which is sort of shaped like a needle, right? So I hope that that is convincing for you to, sorry. Yeah, I hope that is convincing enough for you to sort of agree with me that this rectangular plate will offer you more space than the lower rectangle, despite having the same area, right? And if you're convinced with that, then the reason why a circle will offer you more space than a rectangle, even though they have the same area, is the same, right? That's because the circle has a smaller a smaller boundary length than the rectangle, right, for a given area. So this is also sort of a proof as to how circular symmetry can allow an object to maximize its space for a given amount of material, right? Now this you can quantify mathematically using this parameter. It's just a perimeter to area ratio. You look at the perimeter as in the boundary length of the object, and then divided by the area. So if this parameter is smaller, it offers you more space, right? So you can sort of carry forward this argument in three-dimensional space, but we would accept that the analog of circle in 3 dimension is a sphere, as in sphere is the object that looks the same from every angle, right? So even if the sphere offers you maximum space for that given amount of material, a sphere cannot have any utility in the kitchen for obvious reasons, because you can't gain access to the inner space, right, that it offers. That's one reason. Another reason is it would be mechanically unstable, as in you place a sphere on a table and then you give it a nudge, it will start rolling. So it's not mechanically very stable. But you can, of course, design an optimal shape out of this sphere, let us say by cutting off the top section. Then you have a hole, which now you can gain access to the inner space. And let us say you also cut off the section at the bottom, attach a flat base, so that gives you mechanical stability. So that shape would be optimal. And I think the pressure cooker here is making an attempt to attain that shape, right? But not quite, because at the top it's a little bit cylindrical. Now there could be other reasons other than maximizing space, because if you want to attach a handle, perhaps it's easier if you have a cylindrical structure at the top, right? So, but still, because this object has this axis symmetry, it will offer more space than the objects here, like the cuboid or the tetrahedron, right? So even though it's true that having an axis symmetry in 3 dimensions does not guarantee you maximum space, if you're optimizing not only for space, but let us say for mechanical stability and other things, the object that has the optimal shape still likely is going to have axial symmetry, right? So next time when you're beside a pottery wheel trying to construct a very symmetrical structure, I hope you will sort of remember this fact that you are sort of constructing an optimal shape, right? Optimizing for space, mechanical stability, and the factors. All right, so let me, before I start talking about the forces, let me just briefly talk about rotational motion. Again, this is just basic physics. Because we'll be dealing with a rotating lump of clay, let's briefly talk about rotational motion. So you know that for a body to execute rotational motion, it requires a force that will pivot the body to the center, right? So for example, if there is a body here indicated by the red circle, let us say if it's moving with initial velocity along the vertical direction, in the absence of any force, the body will just go straight up. That's what the Newton's laws say, that it will continue in its state unless acted by an external force. But now, imagine that this body is tied to a string and then somebody is pulling at the point O, right? Then because of the pull, this velocity is it's gonna change its direction. The direction of the velocity is given by this arrow, right? And direction of the force again by this arrow. So the velocity is gonna bend because of the force, right? And then the body will try to move along that new direction, but then again, it's always constantly acted by the force, so the velocity vector will keep bending and bending and bending. Eventually, the body will sort of trace out a circular trajectory, right? And the force that binds the body to this circular trajectory is called centripetal force, right? And the tension of the centripetal, the tension is the source of the centripetal force, right? In this case, in this example. Yeah. So here, if you look at this lump of clay that is stably rotating, there's nothing or no one guarding the clay. And also, it doesn't seem to be attached to any string or, any other, nothing seems to be sort of imposing the circular motion. But then I ask you, so what is making sure that it's sort of stably rotating around an axis? What possible could be the source of the centripetal force in this case? Does anyone have an answer to this? Friction, yeah. So that's right. So at the base, the clay is sort of adhered to the surface of the wheel. And because of that, even if the clay particles sort of try to fly off, it's sort of bound by the friction. All right, so that's the first force that we've encountered so far, the friction force. And we'll see what are the other forces. So to simplify things, let me just broadly divide the stages of making pottery into two phases. One, the preforming phase, where you're trying to position the clay at the center of the wheel, amongst other things. And then you're using that centered clay for the next phase, right? Where you start to sculpt out the structures of your design, which I will call the forming phase. So, so in the preforming phase, again, this is a simplified view. There are two primary objectives. So you're first trying to center the clay. By centering, we mean aligning the center of mass of the clay with the center of the wheel. And the second objective is to homogenize the clay. If there is any, let us say, non-uniformity in the clay due to air pockets or due to cracks, you want to even them out, right, before you start sculpting. So, so you begin by taking the lump of clay and then sort of slamming it on the wheel, right? And so you slam it to ensure that the clay is sort of strongly adhered to the surface, right? That'll give you the friction force for stable rotation. Then you try to sort of move the clay. So even you try to move because after you slam the clay on the surface of the wheel, you do your best to center it, but despite your best effort, it might still not be aligned to the center of mass and the center of the wheel. So you then try to move the clay around so that it's perfectly centered. But for a beginner, as you must have witnessed, and as I also have witnessed, even though without the chance to work on the clay, but sort of just witnessing people work on it, it seems to be sort of a challenge to move the clay, to drag the clay on the surface. One possible reason could be because it's strongly adhered to the surface of the wheel, the clay. The other reason is because, well, you might be thinking that you're doing translational motion because the wheel is rotating at a certain speed. In the reference frame of the wheel, it will not be a translational motion. It's going to execute a very weird motion, which could be very, very non-intuitive, right? So it seems quite to be a challenge to sort of drag the clay on the surface of the wheel when the wheel is rotating. So the best you can do is you can sort of morph the clay and then hope that the mass is sort of symmetrically distributed around the axis, right, to stabilize the clay. Yeah, so but sort of morphing, you're sort of deforming the clay. So you are applying a force, what's called a compressive force, right? So fortunately, I don't have a prop. So I'm just going to use my wallet as a prop. So for example, if I press this wallet from both sides, I'm applying a compressive force, right? So while morphing the clays to evenly distribute the mass, you are sort of applying a compression force, as sort of shown over here. So this is another force that a potter has to grapple with, or make use of, while working on the clay, right? So we've so far we have encountered two forces so far. One is the friction force that provides the centripetal force for for the clay to rotate stably, and then there's compression force that's to deform the clay, right? And then trying to center at the center of the wheel. So, applying a compression force, the only path available for the clay is to go up, because it cannot go in the lateral direction because it's guarded by your hand. It cannot go down because of the wheel. So the only path available is up. Now, the clay that you have played with today during the hands-on session, they might not have been very tall, but some potters, while trying to achieve better homogenization, what they do is they apply high compressive force. And because of that, the clay is sort of raised at a very high level, as sort of shown over here. Right? Because of the high compression, the clay sort of rises, and then it builds a structure which looks like this, right? A clay tower. Now, if you observe this clay tower sort of carefully, you will see that there's a particular shape that it takes. It's not perfectly cylindrical, right? So it's broader at the base and then narrower at the top, right? So it's shaped like a cone, right? So the shape of this clay tower is sort of telling us that the potter is accounting for another type of force. Would you be able to guess what force that is? So is the structure telling us anything about the force that is at play? Why it's not cylindrical, or why it's not any other? So, yeah, right. It's gravity, right? Because you have to realize that the clay at the base is sort of bearing the weight of all the clay top of it, right? So to support that weight, it helps if it has a broader base at the bottom, right? If you invert that structure, let us say you have a bigger circumference at the top and then smaller at the bottom, that's going to be very, very unstable. If you try to rotate it, that's going to sort of bend, and then it's going to be very, very unstable. Right? So that's another force that a potter or you, while playing with the clay, has to account for. So far we have three forces: friction providing this centripetal force. Then you have the compression force to sort of homogenize or sort of morph the clay. And there's gravity that one has to account for when building such tall structures of clay. Now, one has to, once you make such tall clay towers, you have to compress it down, right? And then you repeat that process 2-3 times, according to experts, to attain good homogenization. So while compressing it down, if you just apply the force vertically, then the masses are going to start to accumulate just beneath your hand, right? And then because of the symmetry of the force, you will have a symmetrical distribution of mass around an axis. And the clay structure would look something like this here, shown at the bottom, right? If you apply a vertical force downwards. So this clay structure looks like a mushroom, so people call it a mushroom effect. So now for an expert, that might not matter, but apparently for beginners, having such structures is a problem, because the object of this reforming phase is to homogenize the clay. And such structures, if you do not even out properly, it might, introduce grooves, and then which might further, let us say, introduce voids, and it might not help in homogenization of the clay, right? So to avoid this kind of mushrooming effect, sometimes what experts suggest is you tilt this tower a little bit, and then apply the compression force. So if you, for example, shown over here, you tilt the tower a bit, and then you compress it so that so the tilting sort of breaks the symmetry, the axial symmetry, and then you avoid having such sort of mushroom top tower. So I'll just play a video here and then show you how that is done. Hopefully this will play. Yeah, okay. All right. So yeah, you raise the clay tower and then you sort of give it a tilt, and then you press it. So I'll play that movie once again. So as you form this clay tower, you sort of tilt along the direction indicated by the arrow, and then you compress it. Right? So that seems to avoid this mushrooming effect. Right. So actually, we've accounted for all of the forces: friction, compression, and gravity. But there's one last force that one has to recognize. So while applying compression force to the clay, if the clay is sort of not moving, if it is static, then the only force that the clay will experience is the compression force from your hands, right? But here, the clay is sort of rotating. So because of that, it will experience a shear force, right? Now, what is a shear force? So again, this is my wallet. So compression is just applying the force vertically, perpendicular to the surface, right? Shear would be applying the force tangentially to the body, right? So shearing in this case, I mean, it just deforms the body and that's about it. But in a clay, because it's not as elastic or firm as this wallet, it might rip off the clay particles at the outermost surface, right? So, and which is good if you're looking for homogenization in this phase, right? So you're constantly peeling off the outer surface, exposing the inner surface, and that is being constantly sort of renewed, right, at the outermost region. So which could be good for mixing. And one thing I can say is shear forces actually has wide range of industrial applications. For example, in industries, they use it for mixing chemical solutions and also for grinding materials. So, for example, the blender that you use for making fruit juice, you might think that the sharp blade cutting of those solid fruits is doing the mixing or the shredding, but that is true at the initial part. The blade will sort of cut the fruit into smaller and smaller chunks, but beyond a certain size, it becomes inefficient. Cutting becomes inefficient. So it's the shear between the blade and the fruit pieces, right, that shreds it into finer and finer pieces. So that's about it. So these are the four forces that one can sort of think of that are at play while shaping a structure out of a clay. Now, the last phase is the forming phase, where you're sort of sculpting the shape of your desire. So you begin by making a dent, as you've already seen, and then use that as an initial point to sort of hollow out the inside region of the clay, right? So you eventually get up, let us say, structures looking like this or like that. And one thing that we can realize is, we are making use of circular motion to make such symmetrical objects, right? I mean, without the rotation of the wheel, it might be much more difficult to sort of shape such objects that this kind of symmetry, this even distribution of thickness around the circumference. On a pottery wheel, you don't move your hand around to sort of even out the thickness and then get this structure. The rotation sort of does the job for you. And then you can sort of further process this into different kind of intricate shapes depending on your skill sets. Now, I think Many things can be said about this phase, the forming phase, but because I'm not an expert in pottery making, I'll end it there, right? One might say that there are many important things that goes into this phase. I mean, this is the step where you are working on the clay for the final structure. Right? But because my objective was to sort of tell you the forces involved in pottery making, so I'll just end it there. So just to conclude, I'll summarize by saying that perhaps you sort of appreciated that the structures that you built on a pottery wheel, that can have an optimal shape, right? Shape optimizing for sort of space and stability and so on. And also there are different kind of forces, that is the friction force, the shear force, the compression force, and gravity that are at play while you're sort of sculpting the clay. And the forces have different functions. For example, the shear and compression, you use it for homogenization, and the friction is to give you centripetal force for stable rotation. And so next time, maybe when you're sitting beside a wheel and then working on a clay, perhaps you'll remember these things, and perhaps that will enhance your experience a little bit more. Thank you.
Questions or comments?
The notion of having space in a vessel,
Yeah.
are you referring to some kind of packing density? Or
Just a space available. So packing.
because I would think that area is our measure of space available, right? So if not for area, then what exactly is your measure of available space? Because you're claiming that two things with the same area. Two things may have the same area, but one has more space in some sense. And I understand it in the sense of the strip in which you can't actually place a food item on it if it's not wide enough. Right. So in general, what is this? How does this notion generalize to say a broader variety of shapes that you can make? How do you measure space available?
So I guess it has to do with the packing, how much objects you can sort of place on it. So I don't know how to further simplify this. Yeah, actually, I don't know how to simplify this. So
The other way to think about it is a similar thing, but if you have a fixed vector, what the largest area you can
Right. That
the
was
same.
yeah.
sure. Yeah. So I understood that aspect of it. I was wondering how it is related to this notion of available space. If there was a more formal way of describing that quantity, available space. Thank you.
Soling, are you thinking about a response? Or?
Actually, but maybe I'll get back to but yeah, I can simplify this first.
Is there any other way of making a symmetric object rather than spinning?
I mean, you can apply an object at something home and then rotate it.
So this is the most economic way of making a uniform thickness is the spinning, right?
Spinning the paint is the tray, yeah, the paint.
I mean, I'm just thinking, is there any improvement possible on the potter's wheel?
I'm not sure. I don't think